In this video, we will be solving a problem based on the effectiveness NTU method of heat exchanger analysis. Here, a refrigerator is designed to cool 250 kg per hour of hot fluid with a given CP, which is entering at a 120 degrees Celsius, which is THI, using a parallel flow arrangement. 1000 kilogram per hour of cooling water is entering, which is available at 10 degrees Celsius. Here TCI is also given, overall heat transfer coefficient, as well as area of heat exchanger is given, CPF water given. Here we have to calculate the outlet temperatures of the fluid as well as water, and also the effectiveness of heat exchanger you have to calculate. Means here you are given with only the inlet temperatures of hot and cold. Outlet temperatures are not given, so you cannot apply the LMTD. So LMTD method is failing. Then you can go for the effectiveness NTU method of heat exchanger analysis. So for that, first you will be requiring whichever fluid is having the C minimum value, that is heat capacity rate, which is the product of mass flow rate and specific heat capacity. So for hot fluid, mass flow rate is 250 kg per hour, which is this much kilogram per second, and its specific heat is 3350 joules per kilogram Kelvin. So you will be finding the heat capacity rate of hot fluid as product of m dot h and ch, which is obtained as 232.63 watts per Kelvin. And for cold fluid, mass flow rate is 1000 kg per hour, which is this much kilogram per second, and heat capacity rate is specific heat capacity is this much for water. And you can find the heat capacity rate for cold fluid as 1162.77 watt. So whichever is minimum of the CH and CC, I will be calling that as C min. So here for hot fluid, the heat capacity rate is minimum, so it is C minimum, and the other one will be named as C max. So you will be finding the ratio R or C. In data book, this notation is used. So I will be finding C, which is the ratio of minimum to maximum heat capacity rates. Then I will be getting C as C minimum by C max as 0.2 I will be obtaining. Then I will be finding the value NTU, which is a number of transfer units, which is given as UA by C min. This equation you can find in the data book for heat exchangers. If you are substituting the value of NTU, then you will be getting the NTU value as 1.25. With this value of NTU and C, I can apply the equation for a parallel flow heat exchanger, which you can observe from the data book. The equation is given for a parallel flow heat exchanger. The effectiveness is given as 1 minus e raised to minus n into 1 plus c divided by 1 plus c. I will be applying this equation, where this n is NTU 1.25 and c is the ratio of C min by C max, which is 0.2. Then you will be getting the effectiveness of parallel as 0.46, which you can verify with the plot or graph given in the data book also, where the plot of effectiveness of parallel flow heat exchanger is given. Here the NTU value is 1.25, which will be coming around here, and the ratio of C min by C max is 0.2. So you will be looking the 0.2 curve where it is intersecting this line. So 0.2 curve will be intersecting somewhat here, which if you are plotting, you will be getting, which is around 0.65 you will be obtaining from the graph. Here from the numerical or equation, after substituting, you will be getting 0.646. Just verify that it is around 0.65. Anyway, you will be using this effectiveness for all the other calculations. So one part effectiveness we have solved. Next we have to find the outlet temperatures of both the hot and the cold fluid, for which you will have to obtain the heat transfer, actual heat transfer, for which you will be making use of the maximum heat transfer in the exchanger, which we have already explained that this will be equal to C min into maximum temperature difference, that is THI minus TCI. We are knowing that the C minimum is around 232.65 watts per Kelvin. This Kelvin is actually, or it is same as degree Celsius, so you can substitute this temperatures also in degree Celsius, as it is giving you the change in temperature. This is or degree Celsius into THI is 120 degrees Celsius at which hot is entering and cold fluid is entering at 10. So if you are substituting, then you will be getting the maximum possible heat transfer as 25.59 kilowatts you will be getting. So you are having the effectiveness expression as actual heat transfer divided by maximum possible heat transfer. From this you can obtain the actual heat transfer as effectiveness into Q max, where effectiveness is 0.646 and Q max is 25.59 kilowatts. Then you will be getting this as 16.53 kilowatts you will be getting. This is the actual heat transfer. Using this actual heat transfer, you can find the outlet temperatures of both hot and cold fluid, where this actual heat transfer Q will be equal to, if you are referring the hot fluid, this is equal to CH, this is the product of mass flow rate and specific heat of hot, into change in temperature THI minus THO. This is given as 16.53 or 16.53 into 10 raised to 3 watts. You can substitute this CH is 232.6 watts per Kelvin or watts per degree Celsius. This THI is given, which is 120 degrees Celsius. This is the only unknown. Then if you are substituting, you will be getting THO, the temperature at which hot fluid is entering, which you can obtain it as 48.94 degrees Celsius you will be obtaining. Similarly, you can find the temperature at which cold fluid is leaving, that is the actual heat transfer. You can refer with a cold fluid, where this will be equal to the heat capacity rate of cold fluid into the change in temperature of cold, which is TCO minus TCI. This is again equal to 16.53 kilowatts or 16.53 into 10 raised to 3 watts, where this CC we have obtained in the initial, which is around 1162.7 watts per Kelvin or watts per degree Celsius, as it is change in temperature. TCO we have to obtain, whether TCI is given as 10 degrees Celsius. Then you can find the temperature at which the cold fluid is leaving or water is leaving, that is TCO. If you are substituting, you will be getting as 24.22 degrees Celsius you will be getting. So these are the answers. These are the outlet temperatures, and this is the effectiveness, which is 0.646. Since these outlet temperatures are not given, we cannot apply the LMTD method. So we have followed the effectiveness NTU method, and this is the way how you can solve a heat exchanger problem by using the effectiveness NTU method. Hope you understand. Thank you.